All right, welcome back. This is integration by parts number 2. We're going to do what we did in the last section, integrate by parts, but we're going to introduce something else. It's called the tabular method. Whoa, that's crazy. I let my daughter play with my drawing tool, and I definitely forgot that it changed color and all that stuff. Okay, so we're going to talk about the tabular method in the second example. The first example, we're just going to do another integration by parts. And kind of lead up to why the tabular method might be better. Okay, so integration by parts. So again, we talked about that L-I-A-T-E, the Liat or Liat. I don't know how to pronounce it, but it is what it is. So we're going to do the algebraic, comes before trigonometric. So we get u is x squared, du is 2x dx. And then whatever's left is our dv. So dv is sine of 4x dx. And then the v piece is if I integrate this, you have to, so if I integrate just the sine, I get negative cosine of the expression. But if I think about the derivative of this cosine piece, well, I got to multiply by the chain rule. So I really got to multiply by 4. But if I'm multiplying it by 4, I have to divide by 4 here in order to cancel out, so there's no kind of fraction in front of that. All right, so if you can't do that, then you're going to have to take this, and you're going to say u is equal to 4x, and then du is equal to 4 dx, and then dx is equal to 1 over 4 du, and then you're going to have to go do substitution back in, which is fine. It's just if you can kind of do it in your head maybe a little faster, that might save you some time. So we're going to say the integral of x squared sine of 4x dx is equal to u times v, so x squared times negative 1/4, so actually let me change that, negative 1/4 of x squared cosine of 4x minus the integral of v, which is a minus, which is positive 1/4 cosine of 4x times this 2x. So 2x divided by 4 is x over 2. Okay, cosine of 4x dx. Then if I look at this x over 2 cosine of 4x dx, like we can see that this doesn't play really nice as well. Like I can't really integrate that kind of nicely. So I'm going to make that also a u, v, du, dv, all that stuff. So I'm going to say u, again, my polynomial is x over 2. My du is going to be just 1/2 dx. My dv is what's left, so that's cosine of 4x dx. And then my v is now my integral of this. Well, again, my integral is probably going to have a 1/4 out front because of the chain rule. Because of that chain rule. Let's go. Then we know, okay, I'm going to turn that into x over 2 times 1/4 sine of 4x. So that's going to be x over 8 sine of 4x minus the integral of 1/4 sine of 4x times 1/2 dx. So that's going to be 1/8 over here dx. Okay, so the 1/8 is actually going to pop out front. Okay, I can do that. And now I'm going to integrate sine x. Well, if I integrated sine of 4x, I actually did that over here, okay, in the very beginning. So this is what I get when I integrate it. Okay, so let's kind of move on over here. It's going to be a long answer. Oh, man. Hoo-wee. Let's do this. Let's see if I can do something here. Let's see if I can do something. I can't do what I want to do. So I'm going to write it over here, I guess. Okay, that's cool. So this is really what I want, right? I have the integral of x squared sine of 4x dx, and that's equal to, we know that that's already there, right? So negative 1/4. Well, let's do it over here. So it's equal to negative 1/4 x squared cosine of 4x plus Well, this integral here turned into kind of this piece down here, right? So plus x over 8 sine of 4x minus, well, and then this integral of sine of 4x, like this piece integral here, right, turned into negative 1/4 cosine of x. So that's 1/8 times a negative 1/4. This is actually a negative 1/8. Negative 1/8 times negative 1/4 cosine of 4x. Okay, cosine of 4x. So let's multiply that through. So that's positive 1 over 32 cosine of 4x plus some c. Plus some c, and that is, ladies and gents, my answer to that problem. Now you're like, man, that's a lot of work, man. Why do I do this stuff? Like, why did I get involved in calculus 2? It's actually not bad. That's what we're going to talk about, the tabular method, in the next problem. So let's get to the tabular method. Let's go down to the next problem. All right, here's an example of the tabular method. So I got the integral of x squared sine 4x dx. And so what I want to do is basically create a table. Okay, that's where it's a tabular method, so a method involving a table. And what I want to do, okay, is I'm going to have 3 different columns. So I got sines, I got u, and I got your dv column. Okay, very similar to what we did before, but in this case, we're not just finding the first iteration of your integration by parts, right? We're going to actually, the first iteration doesn't necessarily work. We're going to have to go further and further and further. So if we do this table method, then it's going to help us, I guess, organize our work better, but then also just be easier to find our answer, okay? And so in this case, right, I'm going to make u the x squared term. I'm going to make the dv the sine of 4x term, okay? So I'm going to place that under here, so x squared. This is then the sine of 4x. Okay, if I take the derivative of u, I get 2x, and then 2, and then 0. Okay, so hopefully we can see that. And now, the dv term, I'm going to integrate sine of 4x. All right, well, hopefully we can, again, do this a little bit quicker. And I got negative 1/4 cosine of 4x. Okay, I go one more step. I got negative 1/16 of sine of 4x. And then I go one more step here, and I got 1 over 64th. It's now positive, okay, cosine of 4x. If you need to do the work off to the side, okay, over here, that's fine, right? Basically, we're saying, you know, integrate this, okay, and I'm going to make u 4x, right? Du is now 4, okay, dx, and this is really the sine of u, okay, divided by 4, okay? So this is really 1/4 integral of sine of u. That's basically what you're integrating. And then the next one would be negative 1/4, okay, sine of whatever, right? Or negative 1/4 time, or 1/4 times negative 1/16, or man, I'm getting a little too fast right here. So this one here is basically that one if I integrate it, right? And then the next one, I'm taking another 4th out, and then cosine turns to sine. That's why I got 1/16. And then I'm doing the next one, taking another 4th out, okay, but in this case it's now negative 4th because of the sine to cosine. I got to go backwards that, so you got to think about that. And now with the sine values, okay, I'm always going to start positive, negative, positive, negative. We always have alternating signs. And here's the beauty of the tabular method. Okay, what I'm going to do is, as long as I have these 3 columns in the same direction, like don't change columns, don't put dv here and then u over here. Okay, I'm going to go across and then diagonal. I'm going to go across, diagonal, across, diagonal. Okay, now I'm gonna save one step to the very end here. So what I'm going to do is, once I do the across and diagonal down, I no longer have any integral symbol. Okay, and so let's rewrite this now. I got the integral of x squared sine of 4x dx. That is equal to the very first kind of across and down, So that's negative 1/4 x squared cosine of 4x. Okay? Then I'm going to go to the next one. That's now a minus of a negative, which makes it a positive. 8, it should be 8 in the bottom right. 1/16 times 2 is 1/8. So 1/8 x sine of 4x. Now I go to the next one. That's always it's still a positive. And so that's 2 over 64, so that's plus 1 over 32 cosine of 4x. Now, what happens, the reason why I can stop this way is because this is technically, if I were to make, okay, this across, so instead of going diagonal down, if I went across, then that would be minus the integral of 0 times 1 over 64 cosine of 4x dx. Okay, and I think about that, right? That's 0 times all that. That's just 0. Okay, so that's why that doesn't actually belong there. All right, because it goes away. All right, technically, okay, you could continue down. All right, if I think of, let me erase this. If I were to say, okay, what's this one here? That would be 1 over 256, right? 1 over 256 sine of 4x would be the next one down. I could go that way as well and get rid of the integral. So instead of having minus the integral of 0 times 1 over 64 cosine of 4x, right? I could go down in a diagonal like I have been doing, and I would get 0 times 1 over 256 sine of 4x. And that, again, is just 0. So basically, when you have 0, okay, in this column at the very end, right, you stop in the one previous. Okay, you're going to stop in the step previous than that, because that 0 is just going to cancel everything out. And so that's why it's good that we get 0. Okay, but once I get 0, that means I stop in the U column. Okay, so this right here is our answer. Remember, I have to add the C at the end, but that is our final answer for that tabular method problem, that first problem there. So now let's go on to the next one. All right, we got this one here. It's a definite integral. Okay, definite integral, doesn't matter. It's still the very same process. Okay, again, I have my sine, my u, and my dv. Okay, again, we got to make sure that, right, the polynomial is really what we're going to try to take in the u column here. So u squared minus 1, I'm sorry, x squared, not u squared. X squared minus 1. The dv is e to the x. I integrate this. This is 2x, and then 2, and then 0. Not integrate, take the derivative here, sorry. Integrate this one here, I get e to the x, e to the x, e to the x. That's why e to the x is always great in the dv column. And then, right, plus, minus, plus, minus. Again, I stopped at 0 here. You know, that's why I'm stopping there, okay? If I had another number, then I would keep continuing if I end up canceling stuff. I might not actually get to 0, and that's some other process as well. Okay, so in this case, right, across and then diagonal, okay? Because if I don't go diagonal, if I just go straight across, then what this actually is the integral of x squared minus 1 times e to the x dx. That's the integral, okay? That's what I started with. So if I go across and down, across and diagonal down, that's where I get rid of the integral, okay? And I'm able to then rewrite it as the integral of 0 to 1. Okay, I'm just rewriting the original problem. X squared minus 1 e to the x dx is now equal, okay, to x squared minus 1 e to the x, right? Again, another diagonal and down, minus 2x e to the x, diagonal or across and then diagonal, and then plus 2 e to the x, and then really plus 0, right? That doesn't matter. But all of this here is being evaluated from 0 to 1. Okay, so now I'm going to plug in all my stuff. Okay, I get 1 squared, right? 1 squared minus 1 is 0, so that's just 0 minus, looks like 2e plus 2e. That's cool. Minus, now I plug in 0 to all of this stuff. So 0 minus 1 is negative 1. Negative 1 times 1 is negative 1. That's 0, so plus 0. And then e to the 0 is 1 times 2, so that's 2. Okay, so it looks like I get, that's going to cancel. This is now a plus 1 and a minus 2, so it looks like I get negative 1 for my answer. Okay, that is your final answer there. Okay, so again, we can rewrite that and say, okay, the integral from 0 to 1 of x squared minus 1 e to the x dx is equal to negative 1 because we did all the work here, which is then, and then we ended up with that as well. All right, so that was a definite integral. Now, we're going to go on to the last problem here, which is non-terminating factors. Okay, what does that mean? That means that one of the columns, that u column, is not going to have a 0. Okay, it's not going to have a 0. So let's see if we can figure out how to do this. Okay, I'm going to still use the tabular method. You don't have to. You can use a different method, and you would have to do this multiple times. I'm going to show you using the tabular method here. So we get our sine, we get our u, and our dv. Now this one is definitely harder because, you know, we have to determine what's the best u. Okay, the best u here is going to be sine. Okay, in this case, right, if I take the derivative of e, that really doesn't matter. And if I take the integral of e, that doesn't matter. So that's why I guess it doesn't matter the order in which you put it, because sine is still cyclical. Even if you take the derivative or if you take the integral of it, you're still going to come back around to sine from the beginning. So it doesn't really matter which one you choose. So just be wary of that, okay? So if I take the derivative of sine, right, I get cosine, okay, and then negative sine, and then negative cosine, and then positive sine. So it looks like it comes back around after the fourth iteration. The derivative, or the integral of e to the x, right, is just e to the x. This one's easy. Okay, that one's really easy there. So this is going to be plus, minus, plus, minus, plus, and I could keep continuing to go on. But the problem is that I don't get a 0. There's no 0 in this column. Okay, so I can't just stop. Well, I can stop, but there's a different way we have to do this. Okay, so here's what we're going to do. So I got the integral of e to the x sine x dx. Okay, that's going to be equal, let's start at the very top, right, across and diagonal, right? So that's going to be e to the x sine x, okay, over and diagonal. So that's minus e to the x cosine x. Now, what we can see now is if you look at the next one, okay, if I go across and diagonal like I normally would, you're going to see that this term here is going to cancel out. Okay, and then if you think about it again, if you look over and then diagonal again, this term is going to cancel out. Basically, what's happening is it's becoming cyclic, okay, faster than this iteration down here. It's actually becoming cyclic up here because stuff is canceling out. Basically, if you just kept on doing this and kept on going diagonal or over and diagonal all the way down, you would just get 0 on this side, and you would say, well, the integral of e to the x sine x is 0, right? Because I'm getting 0. Everything's canceling out. Well, this is where the tabular method helps, okay, because then that'll help you determine, like, hey, I can't do that. Okay, so I'm going to erase this one here. And it's becoming cyclic at this negative sine x. So instead of me going over and diagonal, I'm going to go over and across. Now remember from the last two examples that if I go over and across, that the integral doesn't go away. It stays there. So that's the integral of e to the x sine x dx. Well, guess what? This is the same as this, right? So I can manipulate this equation here, right, to add the integral of e to the x sine x dx on the left side. So when I do that, I get 2 times the integral of e to the x sine x dx, which is now equal to e to the x sine x minus e to the x cosine x. And, okay, well, what does that mean? That means that now I can divide this by 2 to solve for it. So I get the integral of e to the x sine x dx is equal to 1/2 e to the x sine x minus 1/2 e to the x cosine x, and then write plus some value c, because it's a non-definite integral, right? So hopefully we can understand that, okay, that I can manipulate it around. So if I were to keep going on a diagonal on this right column and not go across, that you would just have 0 over here. And that can't happen, right? That's not going to be 0. All right, so we got to remember that if I go across and diagonal, I have no integral. But if I go across and across, I still have that integral left over, and then I can manipulate the equation, especially if it's the same integral, right, as what I actually currently need to solve for. Okay, it has to be the same. If it gives you a different integral, then it doesn't matter. Then you got to keep finding the correct one. You got to find out where it becomes cyclic and where that integral then is the same. Okay, and manipulate the equation from there. So hopefully that helps. This is the second, integration by parts, part number 2. Hopefully this tabular method is helpful to you. If you have questions, let me know. But until next time, deuces.